Okay, so the kind of uh, the peak of the course in terms of theorems that we've seen, or if you're measuring maybe in terms of like the depth of the theorems that we talk about, is coming today. So as I've mentioned before, this is a quadratic reciprocity. But before I can state this, I have to define the terms that allows me to state the central thing that quadratic reciprocity concerns. So first, um, well, maybe before I write down this definition, I'll say uh, so far when discussing solving congruences, right? What's kind of the best we can do, right? So up till now we've dealt with linear congruences, right? Like this, um, and that, and certain systems of linear congruences like this are basically that is the extent of the sorts of congruences that we can solve. And so even questions that I could ask you about um, just second order congruences involving an x squared here is something that we haven't really done. We've done it in some very special cases, right? We have a corollary coming back from uh, chapter 6, I believe, that allowed us to solve uh, one of these congruences involving an x squared in a very, very special case. But we haven't really discussed this at all, and that's because in order to discuss this, it requires some more machinery. So what we're discussing then is solving something, uh, that looks like this. So we know what to do here, but here we have big questions, right? I haven't talked about any process for doing this yet. Um, so drawing on your experience from your old algebra background, this is you might expect that something like this is not always something that has a solution, for instance, right? And so questions about whether or not an equation like this has a solution is going to be the topic of the first definition I talk about, which is the notion of a square mod n. So we say that a number a is a square mod n if the congruence x squared is congruent to a mod n has a solution. Okay. Of course, the implication there is that there are going to be instances where an equation like this doesn't have a solution. That is indeed going to be something that happens. Okay. Otherwise, we wouldn't have a special name for it. Okay. All right. So, for example, so a couple of examples. 2 is a square mod 7. Why? Note that 3 squared, which is 9, is congruent to 2 mod 7. And so the equation x squared is congruent to 2 mod 7 has a solution, and that solution is x equals 3. Okay, and minus 1 is a square mod 5. All right, so 2 squared is congruent to minus 1 mod 5. Okay, so that's nice, right? The equation x squared is congruent to minus 1 mod 5 has a solution. Okay, so that's nice. Okay, but 2 is not a square mod 3. since you can just check, right? So 0 squared is not congruent to 2. 1 squared is not congruent to 2. And 2 squared is not congruent to 2, mod 3. And I mean, those are your only options, mod 3, right? So we just exhaustively checked, and none of those things, mod 3 squared, were congruent to 2. So that's it. Okay. So some more terminology here. If A is a square mod n, we say that A is a quadratic residue mod n. If not, it's a quadratic non-residue. Okay. All right. And so, this lays the groundwork for our terminology here. So then there's the following proposition, which says let P be an odd prime. Okay, and let A not be congruent to 0 mod P. Okay, then A to the P minus 1 over 2 is congruent to plus or minus 1 mod P. Okay. Moreover, A is a square mod P if and only if A to the P minus 1 over 2 is congruent to 1 mod P. Okay, so what does this say? This says that if P is an odd prime and A is not divisible by P, right? So A is not congruent to 0 mod P, then A to the P minus 1 over 2 is always congruent to plus or minus 1 mod P. But when this is plus 1, when this is congruent to plus 1, that is exactly when A is a square mod P. Okay. So it's always true that A to the P minus 1 over 2 is congruent to either plus or minus 1 mod P. But the case when A is a square mod P happens only when and exactly when A to the P minus 1 over 2 is congruent to 1 mod P. Okay, so let's prove this. So proof. So let B be congruent to A to the P minus 1 over 2 mod P. Right. Then B squared is A to the P minus 1, right? So this is A to the P minus 1. But hey, by Fermat's little theorem, this is actually congruent to 1 mod P. Okay, so this congruence, of course, is Fermat's little theorem. Okay. Now, we actually have, I had mentioned that we have dealt with solving an equation like this for B, that is B squared is congruent to 1 mod P, This is the only time we've dealt with, quadratic congruences. Okay, and this was from a corollary from chapter 6. So by corollary, I think this is 6.11. So this is from chapter 6. Like I said, this is the only time that we've dealt with this. B must be congruent to plus or minus 1 mod p, i.e. a to the p minus 1 over 2 is congruent to plus or minus 1 mod p. Okay, so that takes care of this bit that says that regardless of what goes on, this is always the case. All right, so if p is an odd prime and a is not congruent to 0 mod p, then a to the p minus 1 over 2 is always congruent to either plus or minus 1 mod p. So now we want to show this if and only if bit that that the plus 1 case is exactly the case when a is a square mod p. Okay, so let's do the forward direction of the if and only if bit. So assume a is a square mod p, okay, i.e. x squared is congruent to a mod p for some x. Okay, thus a to the p minus 1 over 2 is congruent to x squared to the p minus 1 over 2. But this is x to the p minus 1. Aha. But this is 1 mod p. Again by Fermat's little theorem. Okay. So we started with the assumption that a is a square mod p, and then we get that a to the p minus 1 over 2 is congruent to 1 mod p. Okay, so let's do the opposite direction. So assume a to the p minus 1 over 2 is congruent to 1 mod p. Okay, now we're using all of the tools at our disposal. There's a reason why the sections in the chapters are structured the way they are. So let G be a primitive root. Mod P. Okay. Then G to the I is congruent to A for some I. That's part of it being a primitive root. And thus 1 is congruent to A to the P minus 1 over 2, which is congruent to G to the I times P minus 1 over 2 mod P. Okay. But G primitive implies that the order of G mod P is P minus 1, i.e. by the order theorem, what does this mean? So P minus 1 divides I times P minus 1 over 2 by the order theorem. Okay, i.e. just reading off this by definition, this means that P minus 1 times K is equal to I times P minus 1 over 2 for some K. i.e. Since p minus 1s are the same here, I is equal to 2k. It's even, right? Well, this gives you that a is a square mod p. Thus, a is congruent to g to the I, but I is 2 times k. So this is congruent to g to the k squared. So a is a square mod p. And that was all I needed to show. Okay. Okay. And so, this kind of motivates us to consider basically looking at the question of whether or not a given number is a square mod p, and formulating the following classification scheme, or the following notation that allows us to quickly discuss this. So that is the notion of the Legendre symbol. Okay. Okay. So our reason for doing this is that we are interested in trying as best as we can to, figure out as much as possible about when a number is a square mod p, and any other properties that this number has, and we're going to see like what quadratic reciprocity refers to is something that heuristically there's not a whole lot of reason to think would have anything to do with whether or not that number is a square mod p. So it might sound a little bit confusing right now, but I'll go through that once I've stated all these things. So definition, the thing we're defining is the Legendre symbol. So let p be an odd prime, and let a be an integer that's not congruent to 0 mod p. So a is not congruent to 0 mod p. Okay, so define the Legendre symbol as follows. So I'm going to say this is a on p. So think about this like the binomial coefficient, right? Like n choose k. Here, this is a on p. I've heard a Legendre p. I've heard a lot of people say different things here. It's people want to avoid a over p because you use that for a normal fraction, but yeah, there's no like standardized way of saying this. I'm just going to say a on p rather than a Legendre p, which would take me a little bit longer. So this symbol a on p is defined to be plus 1 if x squared is congruent to a mod p has a solution. And minus 1 if it doesn't. Okay. Okay. So this is merely a very convenient symbol for encoding a bunch of info about squares mod p. So using the previous examples, maybe I'll go back to my first sheet here. So in my previous examples, I said that 2 is a square mod 7, because 3 squared is congruent to 2 mod 7. Minus 1 is a square mod 5, because 2 squared is congruent to minus 1 mod 5. But 2 is not a square mod 3, because neither 0, 1, nor 2, when you square them, you get 2, right? So in terms of the Legendre symbol, 2 on 7 is plus 1. Minus 1 on 5 is plus 1. But 2 on 3 is minus 1. Okay. Okay. So, quadratic reciprocity is going to be stated in terms of the Legendre symbol. But before I do that, there is a proposition that I'm going to prove that has multiple parts that contains a part called Euler's Criterion, which is an important tool for understanding the Legendre symbol. But it turns out that due to quadratic reciprocity, when it comes to actually computing these Legendre symbols, which I'm going to do a bunch of examples of that later, when it comes to computing those things, quadratic reciprocity is going to make our lives very, very easy in doing this. But first, I need a proposition. I'm going to fully prove that proposition, and then I will state quadratic reciprocity, and I'm not going to prove it. I will direct you to the proof. I could do it, but it would take me probably an entire lecture to do. So rather than spending a lecture on that, and unfortunately it's one of these proofs that while it's good to see it from a completionist point of view, as far as the goals of this course, you're not going to get really much additional understanding from the proof of it. So anyway, so I'm going to state the following proposition. This doesn't, part of this proposition has a name, but I will, when I refer to this proposition, if we're specifically using it, I will say the proposition right before quadratic reciprocity, unless I'm using this first part. So let P be an odd prime, and let A and B not be congruent to 0 mod P. Then I have a few parts. So the first part is called Euler's Criterion. A on P is congruent to A to the P minus 1 over 2 mod P. Okay, note this is a congruence here. Right? What do I mean by that? Well, I mean, I defined the Legendre symbol, right, as A over P is just straight up equal to a number. It's either plus or minus 1. Okay, and it's plus 1 if A is a square mod P, and it's minus 1 if A is not a square mod P, right? Okay, but here, this is a congruence, right? So the next list of things are not going to be in terms of congruences. They are going to be equalities here. So the next thing has to do with the relationship between multiplying two Legendre symbols with common denominator. So I have A over P times, or sorry, A on P times B on P. Okay, well, Well, this is actually equal to AB on P. Okay. All right. Okay. Another statement is if A is congruent to B mod P, then A on P is equal to B on P. And lastly, and this is important. What I'm going to write out for D here is actually typically included as part of quadratic reciprocity, and I'll state it again when I write out quadratic reciprocity. This is called one of the supplementary laws. So in this case, this is the supplementary law for -1. So -1 on P is equal to +1 if P is congruent to 1 mod 4, and -1 if P is congruent to 3 mod 4. And those are the only options for an odd prime P. Okay. All right, so there's my proposition. So Euler's criterion is this first thing. Second thing says that I can multiply two Legendre symbols, and they're multiplicative in a sense that A on P times B on P is A times B on P. And if A and B are congruent mod P, then their Legendre symbols, the corresponding Legendre symbols for them are congruent. So A on P are equal. A on P is equal to B on P. And then this last one tells me a quick way of saying whether or not -1 on P is +1 or -1. So if P is congruent to 1 mod 4, it's +1. If P is congruent to 3 mod 4, it's -1. Okay, so let's see why these things are. Okay. So if A is a square mod P, then by the previous proposition, let me just remind you. So the previous proposition said A is a square mod P if and only if A to the P minus 1 over 2 is congruent to 1 mod P. Otherwise, A to the P minus 1 over 2 is always congruent to plus or minus 1 mod P. So narrowing this down tells me exactly what's going to happen if A is not a square mod P. That's the point. Right, so this is exhaustive. So I could have stated this in another way. A is not a square mod P if and only if A to the P minus 1 over 2 is congruent to minus 1 mod P. Okay. So A is a square mod P. Then by the previous proposition, A to the P minus 1 over 2 is congruent to plus 1, right, which is equal to A on P mod P. Okay. If A is not a square mod P, then similarly A to the P minus 1 over 2 is congruent to minus 1. But the way the Legendre symbol is defined, of course, is that if A is not a square mod P, then A on P is minus 1. So this is also A on P mod P. Right? So in either case, whether A is a square mod P or not, this thing is congruent. A to the P minus 1 over 2 is congruent to the Legendre symbol A on P mod P. Okay. So that's A has been proven here. Maybe I'll annotate that. I've proven A here. So that's Euler's criterion. The B part. So how does this work? Well, Euler's criterion, now that we've shown it, so Euler's criterion holds for both A and B, since there's no difference between our assumptions of A and B, just reminding you. Right, so yes, we stated Euler's criterion for A, but obviously I can swap B in here and nothing changes. So Euler's criterion holds for both A and B, thus, I mean, it also holds for AB. Maybe I should include that. And also AB. Thus, I get a string of congruences here. So A on P times B on P by Euler's criterion. This is congruent to A to the P minus 1 over 2 times B to the P minus 1 over 2. But of course, that's just equal to AB to the P minus 1 over 2. But by Euler's criterion, this is congruent to A times B on P mod P. So I have something I have to say here. To prove B, I have to prove that these two Legendre symbols are equal, right? Okay, so I have to show that these are equal. What have I shown? I've shown that A on P times B on P is congruent to A times B on P mod P, which is not quite the same as showing that, well, at least not immediately the same as showing that A on P times B on P is equal to A times B on P. But why is this actually the case, right? So, well, both ends are plus and minus 1, right? Whatever these are, the only possible values a Legendre symbol can have is plus or minus 1. So whatever this is plus or minus 1. Whatever this product is, it's plus or minus 1. And so I have a string of congruences. These two things are congruent. And in either case, they're congruent to plus or minus 1. But in order for them to be equal, right, they just have to match up. And they have to match up because plus and minus 1 are not congruent to one another mod P, right? So because P is an odd prime, so it's at least 3, right? But since P is at least 3, minus 1 is not congruent to plus 1 mod P. So the only way that this congruence can happen is if they're in fact equal. Okay, that's the reason we had to say this. Okay, so we have equality. Not just the congruence statement. Okay. All right. So that's the B part. Okay, so continuing on. So let's do the C part. Well, so if A is congruent to B mod P, I want to show that A on P is the same as B on P. Okay, then x squared is congruent to A mod P has a solution or doesn't have a solution. If and only if x squared is congruent to B mod P has a solution. Right. Thus, A on P has to be equal to B on P. Right? If A is a square mod P, then so is B. Okay, so both of these would be plus 1. And if A is not a square mod P, then B also wouldn't be a square mod P, and so both of these would be minus 1. So that's it. All right. So the proof of D. Note, P minus 1 over 2 is even if P is congruent to 1 mod 4 and odd if P is congruent to 3 mod 4. Thus, minus 1 on P is congruent to, by Euler's criterion, minus 1 to the P minus 1 over 2, which is equal to plus 1 if P is congruent to 1 mod 4, and minus 1 if P is congruent to 3 mod 4, which is exactly that statement. Okay. So that proves my proposition. Okay. So another useful fact, maybe I'll add a star here, another related fact, and this is nice. This is useful for a number of reasons. I didn't say it as part of the proposition, but it deserves to be mentioned alongside it. So note that x squared on P is equal to 1 if P does not divide x. Why? Well, x squared is automatically a square mod P. Quick proof of this using so you might say, oh, well, if P doesn't divide x, yeah, x squared is automatically a square mod P. But another way of seeing this is we can just see it directly from this proposition that we just showed. So x squared on P can be written as x on P squared. X on P, whatever it is, it's plus minus 1. So it's plus minus 1 squared, which is 1, right? There it is. And so, reading this is if P doesn't divide x, then x squared is always a square mod P. Okay. So it might seem, fairly obvious here, but this can still be very useful. Okay. So now for the big time. Okay. On to quadratic reciprocity. Okay. So this is definitely the deepest theorem that we'll talk about. Well, not just that we'll talk about, but it's the deepest theorem that we are going to talk about in a sense that we could actually prove this. As I said, if I were willing to devote an entire lecture to it, this is the contents of 13.5 in the textbook. It's something that doesn't need any other machinery to prove. So like basically what you know currently is enough to get the job done. So it is certainly the deepest theorem we'll talk about like that. And the theorem itself has spawned a gigantic amount of work in generalizations of it, and also served as motivation for the development of huge, vast parts of the various branches related to number theory. So, so quadratic reciprocity is something. It's like if you had to choose to delete, most of your knowledge of the course, this is the thing you wouldn't want to delete, because this is kind of like the highlight of an undergraduate course in number theory. Okay, so this is it. So I'm going to phrase it as 3 parts. So P and Q be distinct primes. And we want them both to be odd. Okay. So let P and Q be distinct odd primes. Then Q on P is equal to minus 1 to the P minus 1 times Q minus 1 over 2. Or sorry, not over 2, over 4. Yeah, that's key. Times P on Q. Okay. Now, before I state anything else, okay, this is saying that there is some proposed, relation here between when Q is a square mod P and when P is a square mod Q. And one of the reasons why quadratic reciprocity is so deep and so amazing and miraculous in a way is that, heuristically speaking, if you're just like thinking, right, trying to develop your intuition here, there's just almost no intuition for why Q being a square mod P would have anything to do with P being a square mod Q. There just seems to be no good reason why that would be the case, just thinking about it. Okay, so this is one of the reasons why it's considered, miraculous. So, i.e., writing this in a nicer form. So Q on P can be written as, so basically I'm thinking, when is this going to be 1? Right? So sometimes this would, minus 1 to this power, whatever it is, would be 1. And in that case, Q on P would be the same as P on Q. Right? They would match up. Okay. Well, what has to occur here? What if P minus 1 is divisible by 4? So if P minus 1 is divisible by 4, then what I'm left with is minus 1 to some integer, so something times Q minus 1. But Q is an odd prime, so Q minus 1 is even, so I have even times some integer, so that's even, minus 1 to the even, so that would be 1. So that would be true if P minus 1 was divisible by 4, or if P was congruent to 1 mod 4. But notice it actually doesn't matter which of those would be, whether P minus 1 is divisible by 4 or Q minus 1 is divisible by 4, we would get the same thing. Of course, if both of them was divisible by 4, even better. So this is, this holds. So this is actually 1 if at least one of P and Q is 1 mod 4. And we get that Q on P is minus P on Q when that doesn't happen, when neither of them is 1 mod 4. But if neither of them is 1 mod 4, then both of them have to be congruent to 3 mod 4. And so this is true if P is congruent to Q is congruent to 3 mod 4. Okay. And so in either case, right, so in the first case, if one of P and Q is congruent to 1 mod 4, then what this is saying is that when Q is a square mod P and when P is a square mod Q exactly match up, right? So when they are and when they aren't exactly match up. And if P and Q are both congruent to 3 mod 4, then these swap, right? So if Q is not a square mod P, then P is a square mod Q, and vice versa, right? Um, okay. So this is the main statement of quadratic reciprocity. Okay. The two remaining statements are called the supplementary laws. They are included. And they are included because, practically speaking, for computing these Legendre symbols, we're going to use these quite a bit. So supplementary laws, if I called that part A, part B is let P be an odd prime. Then minus 1 on P, we've already seen, is minus 1 to the P minus 1 over 2, which is plus 1 if P is congruent to 1 mod 4, and minus 1 if P is congruent to 3 mod 4. Okay, so we've actually proven this part of quadratic reciprocity. That was D from the previous proposition. Okay, and then C, let P be an odd prime. The reason I'm stating these separately is that these supplementary laws you are often going to use to compute Legendre symbols, even if you don't explicitly use quadratic reciprocity. So then 2 on P is minus 1 to the P squared minus 1 over 8, which is plus 1 if P is congruent to 1 or 7 mod 8, and minus 1 if P is congruent to 3 or 5 mod 8. For a prime P, those are the only possibilities. Okay. All right. So these are called the supplementary laws, or specifically the supplementary laws for minus 1 and for 2. Okay, and the statement of quadratic reciprocity is this main bit that I've listed in part A. Okay. So, just a little bit of history here. So, quadratic reciprocity was, it was first conjectured by Euler in like 1740s, and Legendre in the late 1700s. And then in 1796, when Gauss was 18, he gave the first proof. He published more proofs, I think like 6 more, and then they found 2 further in his writings. And there's currently, I don't know how many published proofs there are of quadratic reciprocity, but this has become kind of like a fun thing, trying to come up with another proof of quadratic reciprocity among mathematicians. So there's tons of proofs of quadratic reciprocity now. And as I mentioned previously, trying to generalize quadratic reciprocity is in large part what inspired a huge amount of development of algebraic number theory in the resulting centuries. So this is something that it is very much a central part in the development of number theory. So the textbook gives the following analogy. It says, consider congruences in like linear Diophantine equations being at the easy level, where so everything we've encountered in this course, if we consider that the base level, right, it's like Gnostic level 1, then the results aren't that surprising. They're pretty straightforward. All the proofs that we did in those, nothing crazy was required to prove any of that stuff. But even though, they are in some ways obvious or more trivial than some of the stuff that came later, they're still important, obviously. You gotta start somewhere, and those applications of those things, we still use that throughout all these proofs. And then kind of the next level would be Fermat's little theorem and Euler's theorem, those sorts of things. And then this is on another level from those previous things that we did in chapter 8. And I guess the best reasoning for this is just if you like try to think about it, heuristically there just doesn't seem to be any reason why Q being a square mod P would have anything to do with P being a square mod Q. It just doesn't seem like they would necessarily even be related. So, okay. So then what does quadratic reciprocity allow us to do? Well, notice that I defined the terminology surrounding a number being a square mod P. But apart from the very easy examples that I cooked up, we didn't ask a single time whether or not, say some number was a square mod some other number. I didn't do an example of anything more involved than like single digit numbers. So what if I wanted to ask the following? Like, is 23 a square mod 419? Okay, well, what would I compute to check this? Well, I would compute the Legendre symbol, right? So I am looking for 23 on 419, right? I want to compute this Legendre symbol. Any Legendre symbol you're computing, the only possible answers are +1 and -1, right? And so this will answer in the affirmative if it's +1, and if it's -1, it'll answer in the negative. So I just want to get an answer for this. I just want to see, is this +1 or -1? Well, what can I say? Using quadratic reciprocity, I can say that this is equal to minus 419 on 23, right? By quadratic reciprocity, since 23 is congruent to 419, which is congruent to 3 mod 4. So both of these things are congruent to 3 mod 4, and so we are in the exact case in quadratic reciprocity where we get the flip with the minus sign, right? So just to remind you, so Q on P is minus P on Q if both P and Q are congruent to 3 mod 4. If one of them is congruent to 1 mod 4, then when we flip, we don't have to introduce the minus sign, right? Okay. All right, so now what do I want to use? So now I want to use a fact from the previous proposition, or I should say the proposition immediately before quadratic reciprocity. So here's that proposition. I want to look at this and see how I can use this to my advantage. Well, this would be nice if I had a number I could factor, but I'm dealing with a bunch of primes here, so I'm not gonna worry about trying to factor stuff. But this can be useful for later. In fact, we'll do this here in a second. What about this? This says if A is congruent to B mod P, then A on P is equal to B on P. Oh, well, that is useful because that means I can reduce this larger number, 419, mod 23, to something that's more manageable, and it would have the same Legendre symbol, right? So this is actually equal to minus 5 on 23, since 419 is congruent to 5 mod 23. Right. Okay. So now what? What is it that I'm going for here? Right. So the idea is I want to reduce this Legendre symbol to involve numbers that are small enough that I can just spit out the answer. or that they are in a particularly nice form that I can just spit out the answer. So I will get into that in a second in another example. Here, you'll see where we're headed with this. So what I want to do is I want to flip again, right? So I want to flip again using quadratic reciprocity. So 5 is congruent to 1 mod 4. So when I flip, I don't have to change the sign. So this is minus 23 on 5, right? And that's by quadratic reciprocity, since 5, we only need one of them to be congruent to 1 mod 4. Okay. Okay. But now I can do this trick of reducing this mod 5 to use something that's more convenient for computing Legendre symbol. So mod 5, this is 3. So this is minus 3 on 5, since 23 is congruent to 3 mod 5. Okay. All right. But again, I still have 5 involved here, which of course is still congruent to 1 mod 4. So I can flip again without changing my sign here. So this is minus 5 on 3 by quadratic reciprocity, since, again, 5 is congruent to 1 mod 4. All right. Reducing again, this is minus 2 on 3, and that's since 5 is congruent to 2 mod 3. Okay. And this is minus, what is 2 on 3? Well, we have now reduced it to a Legendre symbol I can just read off. Right? What do I mean? I can use the supplementary laws, right? So supplementary laws for 2 says that 2 on p is minus 1 to the p squared minus 1 over 8, which just means that it's plus 1 if p is congruent to 1 or 7 mod 8, and minus 1 if p is congruent to 3 or 5 mod 8. So here I have 3. So I have 2 on 3. 3 is definitely congruent to 3 mod 8, and so this is a minus 1. So this is minus 1 by supplementary law for 2. So this is 1. So 23 is a square mod 419. Okay. So we were able to use the Legendre symbol and quadratic reciprocity to answer in the affirmative. Yes, this is indeed a square mod 419. Now, it should be noted, right? Note, while this gave us an answer to the question of whether x exists such that x squared is congruent to 23 mod 419, it didn't actually solve for such an x. All right, i.e. this process is an example of something that's non-constructive, right? So the process doesn't simultaneously construct the solution for you. It just tells you whether or not a solution exists. Okay, we'll see later how we can find such an x. In fact, 182 squared is congruent to 23 mod 419. Okay. All right. So we do have such an x that is that gives us this solution, but this process we used didn't find it. It just said whether or not there was a solution in the first place. Okay. Okay, so I think that is a good place to stop here, and I'll do more of these examples tomorrow. So this is we're entering the home stretch in terms of what is left for us to do. So I'll do more examples of quadratic reciprocity stuff, how that can be used. I'll go into just a little bit the specifics of, in some cases, how you have a formula for square roots, mod p, and solving quadratic equations, mod p. But then after that, we'll be done with chapter 13. We'll have a brief stop in chapter 14. I promised to talk about primality testing. That is, what if you need to come up with a 100-digit prime, right? What do you do in that instance? So I will do a brief stop with that sort of stuff, and then we'll do Minkowski's theorem, chapter 15. By the time we finish that, we'll have probably a couple extra days left over, which I'll either use for review or I'll use maybe one of those days to talk about a nice some extra topic like elliptic curves or something. So anyway, that's the plan. So I will see you all tomorrow.